about 50 nanometer or so, we begin to see viruses. If you multiply 50 nanometer by 1,000, you come to the thickness of your hair. Hair, I just put here, human hair is about 60 to 120 micrometer wide. It's much, much larger than the nanotechnology, the upper limit of the nanotechnology. So we are in a region which is very small, very difficult to view unless you use the electrons to help you. It's very difficult to manipulate. And so far, in the history of science and engineering, this range was not used. There were nanoparticles, there were nanostructures, but humans have never explored there cognitively. Only now, in the last 10, 15 years, we started manipulating things, controlling the processes at that range. And that started giving us a very rich engineering and science opportunity. Many of the fundamentals are not well understood in this range. And because of this, there's a huge challenge. It's different than the typical engineering challenges we have. I like this slide a lot. This slide was prepared by Mike Rocco a few years back. And Mike Rocco has started the National Nanotechnology Initiative along with Richard Smalley and a number of other key researchers. His contributions to the field has been significant. And I'm proud that he was a member of faculty at the University of Kentucky when I joined the University of Kentucky. Now, in this slide, you see two important lines which are critical to study. Well, first of all, this axis is the decades starting from 1940s, 1940, 1960, 1980, 2000, 2020. So roughly we are here, just about this place where these two lines converge. What you see in the below is the realm of the physics, chemistry, and mathematics. Quantum mechanics started at a very small range, and this axis shows you the length scales. So the quantum mechanics was involved with 1 angstrom and maybe smaller range. And this study of quantum mechanics, single molecules by chemists, and understanding the mathematical behavior of different suborbital particles, they have been explored since 1940s. But they could not go beyond a size range because it was difficult to model. It was difficult to combine them. Slowly, with the advances in computers, advances in the algorithms, creative algorithms, physicists, chemists, and mathematicians started increasing their range of applicability. And in these days, they are close to about 10 nanometer, 20 nanometer range. On the other hand, physicists, mechanical engineers, electrical engineers, biologists, they have been studying much larger systems. With the advances in the diagnostic tools and characterization tools, they were able to identify the smaller features of each and every element, and they were coming slowly down. And in these days, in the last 10 years or so, they were able to go below 100 nanometer. They were able to develop models to understand what was going on below 100 nanometer. Suddenly, we started seeing that all these groups can start working together in a realm which is below 100 nanometer or so. That was a natural evolution of sciences. We came to this point. Now, at this point now, we will begin to see the joint collaborative studies by these people from different disciplines would allow us to explore completely new areas. Well, one of them which is emphasized here is the system creation. In the long run, it will be more about the biomimetics, which is the simulations of nature, robotics, guided assembly, evolutionary studies. All of them will be part of the nanoscale sciences. At this side of the slide, you see 2000, 2010, and 2020. These are predictions, how the developments in the field will proceed. Up until 2000, we have been talking about passive nanostructures, just like what you see in stained glass windows. The colors are different from red to blue because the particles are different sizes. But what would you do with them? Can you really use these color changes to your advantage to manipulate these particles and build manufacturing systems where you can put the particles together as you want, as you wish? And the systems of nanosystems will follow up, and finally we come to molecular nanosystems. I think all these are very active, very interesting ideas. So there's always a question. Today is nanotechnology. Do you think next year, 5 years down the road, 10 years down the road, are we going to see the same kind of hoopla, same kind of energy for auto technology or for any other technology? Interestingly, nanotechnology is unique because if you look at this slide, right in this area, you'll begin to see that the length scale also corresponds to the length scale of DNA. This is the engine of life. At this point, life sciences and physical sciences nicely converge, and there is not much understood. There are so many things that we know we can do, but interestingly, we don't know many of the things. So given that, I would like to show you 2 slides, and these are just to observe nature and what the nature is providing. So I have to apologize. For some reason, my computer doesn't allow me click on these pictures to show you the movies, so I will just go to outside to show my videos. Well, one of them is about a climbing gecko. As you know, well, there are geckos everywhere. You see them, and they are fast, amazing creatures. And look at this guy, how quickly it can climb. It's only if I slow down the movie, I can start seeing it going up. And these geckos can go everywhere. And the reason that this guy can climb this fast is because of its small hair in its hands that allow the force applied and released very cleverly over the time. Indeed, I'll show you at the end what the engineers are able to do, but for the moment, just observing its ability to climb is impressive. The next video I will show you is a little bit different. I'll just show, then I'll talk. This is about an octopus. This is how an octopus can hide itself. This is the reverse of the same movie in slow motion. It can go and hide itself completely. So can you imagine engineering a system like this? Can we really do this? Interestingly, we are able to do similar things, not necessarily to this extent. It will take maybe another 100 years before we can make it as efficient as an octopus. Maybe we will never do. But how can it do? Indeed, how can it change its appearance? Well, let me go back to the presentation.